Baik, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang semuanya, selamat datang untuk semua partisipan yang hadir di auditorium MRPQ Kampus UI Depok dan juga peserta online yang ada hadir melalui Zoom. Selamat datang di acara kuliah tamu pada hari ini, tanggal 15 Februari 2024, dengan kuliah tamu yang menarik dengan tema Cellular Concept and Mobile Radio Propagation dan Antenna Array and its Application in Smart Antennas. Sebelum saya mulai acara hari ini, saya ingin memberikan sambutan hangat kepada pembicara tamu kita, yaitu Profesor Dr. Sharul Kamal Abdul Rahim dan juga Associate Profesor Dr. Norhudah Seman. Selamat datang di Universitas Indonesia, Prof. Profesor Sharul Kamal dan Dr. Norhudah adalah ahli di bidang microwave engineering, antena, beamforming, dan smart antena. Jadi pada kuliah tamu hari ini semoga kita bisa mendapatkan ilmu-ilmu baru ataupun insight mengenai teknologi tentang antena dan juga microwave engineering, baik untuk teman-teman di kuliah di S1, S2, S3 ataupun researcher dan akademisi lainnya. Acara ini akan dibagi menjadi 3 sesi. Sesi pertama itu akan diisi oleh Profesor Sharul Kamal, lalu kedua akan dilanjut oleh Profesor Norhudah. Setelah itu baru kita akan melanjutkan dengan sesi Q&A. Sebelum kita mulai dengan Profesor Kamal, akan saya bacakan dulu sedikit CV beliau. Profesor Sharul Kamal Abdul Rahim obtained his first degree in electrical engineering from the University of Tennessee, USA in 1996. Building on this foundation, he earned his Master of Science in Communication Engineering from Universiti Teknologi Malaysia, and later pursue a PhD in wireless communication system at the University of Birmingham, United Kingdom, and completing his doctoral studies in 2007. Since 2001, he has been a valuable contributor to the Wireless Communication Center at UTM, a distinguished High Center of Excellence, or HICoE. His journey in academia follows a successful stint in the industry, where he gained 3 years of practical experience before joining WCC. Recognized for his significant contribution, he achieved the rank of associate professor in 2010 and was subsequently promoted to the position of professor in 2017. His research focus encompasses antenna design, smart antenna system, and beamforming network communication. With an impressive scholarly profile, he holds an H index of 29 according to Scopus, with over 3,553 citations. He has authored 21 books and book chapters and has published more than 280 technical papers in reputable journals and proceedings, including IEEE Transaction on Antenna and Propagation, IEEE Antennas and Wireless Propagation Letter, IEEE Antenna Magazine, IEEE Access, and Electronic Letters. Beyond his academic endeavors, he has been a sought-after speaker at international conferences, serving as keynote, plenary, and invited speaker. He has also chaired sessions at numerous conferences, showcasing his leadership in the academic community. In recognition of his excellence, he has received over 56 academic and research awards. As a testament to his research capability, he has secured more than 41 research grants both internationally and nationally. Leading as the head of various projects, his innovative work is further reflected in 11 granted patents and over 15 copyrights. His professional achievements extend beyond the academic realm. He became a registered professional engineer in 2010 and actively contributes to the Engineering Accreditation Council of the Board of Engineers Malaysia as member of the Senior Evaluation Panel. And as an adjunct professor at the University of Swinburne, he continued to share his expertise with wider academic community. His involvement in the institution engineer Malaysia Southern Branch, including roles. So, for Professor Sharul Kamal, let's begin our first session.
Okay, Bismillahirrahmanirrahim. Alhamdulillahirrabbilalamin, wassalatu wassalam asyrafil anbiya wal mursalin wa ala alihi wa sahbihi ajmain. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera ya. salam persahabatan ya antara Malaysia dan Indonesia. Okay. So allow me to convey my presentations in English. Yeah. Okay. First of all, I would like to thank Master of Ceremony. Yeah. And I also would like to thank Prof. 3, yeah, and the team, yeah, for inviting us, yeah, to share, yeah. I will say a little bit of our knowledge, yeah, with all the students here, yeah. So as it mentioned by the MC, I think we'll be given about 30 minutes for the presentations. So based on my visit to the lab and discussion in the morning, I will say that 30 minutes, yeah, will not be adequate lah, yeah, for us to to teach, yeah, because I will say that, you know, with 30 minutes, I think we can just share. I'm not here to teach, because I think with the respective professors that you have here, I think you are actually good enough lah. Okay, all right. Nevertheless, okay, my name is Sharul Kamal bin Abdul Rahim. So the title of my presentation today, yeah, is Cellular Concept and Mobile Radio Propagations. Yeah. So I hope that with my small presentation here, I think we will be able to gain, you know, some small knowledge. Yeah. Okay, basically the reasons why me and Dr. Huda are here is because of the collaborations, yeah, between UI, University of Indonesia, and UTM. And for your information, currently we have a matching grant, yeah, between both universities, yeah, and basically, but Prof. 3, yeah, she came to UTM, I think sometime on November, right? Yeah. So that's why we are here today, yeah, to pay back lah her visit, yeah, to UTM, yeah. So basically, this is actually the title of our of our proposals, yeah. So basically, from here, maybe it will be better for me to move a bit, yeah. Okay. So basically, from here, so this is actually the title of our presentation today, the title of our project proposals. And in the morning, we had Dr. Adia, yeah, to give his presentations, yeah. And this is actually the team, yeah, which consists of team from UTM as well as UI, yeah. And this is something that we have been working on right now, yeah. Okay, so for today's presentation, basically I'm going to give a little bit about some introductions about UTM, yeah, as well as about residential college in UTM, yeah. And for information, basically in UTM, I would say that all of our mahasiswa, yeah, is actually staying for undergraduate. They're actually staying inside the campus. Yeah? So basically, all the students are staying inside lah. Yeah, and later on I'm going to go to the cellular concept, yeah, mobile radio propagations, yeah, as well as on the case study on the Asian Evo project. For your information, basically currently I'm actually heading one Japanese grant, yeah, under they call it as the Asian Evo project. So I'm going to explain a bit what we have been working on this grant, yeah. All right. First of all, basically, I would like to explain a bit about UTM. Maybe some of you have heard about UTM before, but maybe some of you have not heard of UTM before, lah. Yeah. Okay. Yeah. Okay. Sorry. Thanks. Okay. So basically, UTM was started, yeah, as a technical school in 1904. Yeah. So basically, when I did my study in terms of UI, I know that I think UI have been started much more earlier than us. I think in 18 something, yeah. But us, we started in 1904, but as a technical school. And later on, I think we have been upgraded to become the technical college in 1946, yeah. Then become the National Institute of Technology in 1972. and eventually become the university in 1975. So basically, if they say we look into the history of UTM, basically we can see that we are still a young university, compared to UI. And for your information, basically in Malaysia, we have 20 public university, and we have about 30 private university, and UTM is one of the 20 public university that we have. And in terms of the okay, I'm going to show about the what do you call that, about the ranking. So this is something that I think we've been talking about I think in the morning about the world ranking. So based on my literature review, right? Based on my literature, I found that in Indonesia you have many great universities, and one of them is UI. But in terms of ranking, basically UTM we have quite a good ranking. For example, in 2024 our ranking is 188, and I think in UI I think you have maybe about 200 or 300. But for us we actually 188. And we actually rank number 13 in top 50, top under 50. Under 20 means universities which are 50 years or below. So we actually rank number 13. And basically, in terms of the subject, so basically we actually top 100 for the engineering. And we actually, what do you call that, number 1 in Malaysia for the architecture, as well as for engineering, civil and structure. So this is about us for the ranking. And in terms of the location, basically we actually located in 3 different areas. The first one is actually in Kuala Lumpur. So basically this is our first campus, which is located in Kuala Lumpur. And the area is very small, about 35 hectares. And our main campus is actually located in Johor Bahru, which is actually at the southern tip of the Peninsula of Malaysia. So the distance between our campus to Singapore is about 20 kilometers away. So usually those actually traveling to Singapore, and they will visit us, some of the professors. And our third campus is located in Pago, which is in between Johor and Selangor. So this is actually where we are actually lah. So about this campus, this is actually they call it as a city campus, where the distance to the KLCC is I think around 1 kilometers away, which is very, very close to the city center. Okay, in terms of the number of students, basically we have about 16,000 students for undergraduate, 9,000 for the postgraduate, so total about 25,000, and we have about 5,000 what do you call that, international students, and most of our students, or majority of students, of this international, I would say one of the top is actually from Indonesia. So basically we really encourage you to come over, maybe to visit us, who knows, maybe can also join us. And in terms of the academic staff, basically we have about 1,600 academic staff, about UTM. Okay, so as I did mention to you, basically in UTM, basically all of the students we actually staying, they are all staying inside the campus. So in total we have 11, what do you call that, residential for the students, college residentials. So 10 in Johor Bahru and 1 in Kuala Lumpur. So basically all the students, they will be staying inside the UTM. So this is UTM itself. So this is actually UTM itself. So you can see 10 colleges are located around this. I would say Dewan Kuliah. So Kuliah is in center. So these are all the what do you call that? The student halls. And for the KTC, which one of the colleges, as I told you, I'm actually in charge of the student affair. So basically, I'm staying inside in one of these colleges. So the college that I stay is called College Johor Chancellor, and this college is actually very close to the Faculty of Electrical Engineering. Yeah, so basically the student will be able just to cross or to walk lah, yeah, to the Dewan Kuliah. Yeah. Alright, so now what I'm going to share with you today is actually about the cellular concept. Yeah. Okay, according to the American, psychologist named Abraham, yeah. So basically, according to him, in order for us to survive, yeah, we need 6 basic needs. Yeah, for example, we need air, sleeps, shelter, safety, water, yeah, as well as food. Yeah, but when I did a survey to my student, yeah, he said that the most important things that we need is actually a smartphone. I'm not sure whether that one is true or not, yeah, but this is actually something that based on my survey to my students. Yeah, why is it? Yeah, the reason is because they say we can see every day, whenever we wake up in the morning, yeah, then we can see that the first thing that we will see is actually our smartphone. Yeah, we will open our WhatsApp, we will open our email, so to check is there anything. Yeah. So basically, what we can see that handphone is actually a very, very important thing. Yeah. So this is where cellular takes its place. Yeah. So when we are talking about first mobile phone system, yeah. So basically, the first mobile telephone system was developed in US in 1945. So basically, in this system, so you can see that it consists of very tall tower, and the transmitted power that is transferred is actually very, very high. And the reason is because it needs to cover the whole of this area, and because this is the only area that have the coverage. So whenever the people are actually within this coverage area, then he or she will be able to communicate. Yeah, but those actually outside this area will not be to communicate. Yeah, one of the example that have a very tall tower, is let's say you travel to Paris, and we know they have like Eiffel Tower. Yeah, so Eiffel Tower is an example of a very tall tower that is used for the telecommunications. Okay, and this is actually the first mobile telephone system. Yeah, so you can see in this system, why they call it as a mobile radio, because it has a radio unit and it is actually attached to a car. So whenever the car is actually moving within this area, this is actually why we call it as a mobile radio. And this is actually how it looks like. Yeah. Then, there is actually an introduction of the cellular concept. Okay, so we are talking about the smartphone, right? Yeah, mobile phone, yeah. So the cellular concept. So what is actually the cellular concept? Yeah. So basically from here we can see that cellular concept play a very important roles, in order to solve the problem of capacity as well as congestions. Yeah, because whenever we have only one and only tower just now, or one and only cell, then we will not be able to cater for so many users. Yeah, and there is certain limits on how many users can cater for only one tower. Yeah, so by having this cellular concept, basically we are able to break through the problem of congestion as well as in terms of the capacity problems. Yeah, so how this concept works? Yeah, basically the concept works when instead of having one and only tower, now the area is actually divided into several cells. Yeah, and each of the cell will be having its own radio base stations. Yeah, you can see this is one cell, second cell, third cell, and fourth cell. Yeah, so whenever the users are within this cell, it will be able to communicate with this respective RBS. Yeah, but whenever we travel, for example, in the morning I travel from Jakarta Central to here. So basically, I have to go through what area? Yeah, meanings I have to travel from one cell to another. So in order for us to have a continuous communications, then there will be a concept what we call as they call as a handoff. Yeah, whenever we actually moving from one cell to another, then the control of the system, will be hand over to the adjacent cell. This is actually what we call as a handover concept. Okay. All right. Now I think I would like to explain about the evolutions of wireless mobile communication. So basically, as we can see, what do you call that? Mobile communication started in 1980, where this is actually we call it as a first generation of mobile communications. And basically the system, it use analogs, based system, and later on in 10 years later in 1990s, 2G was introduced. So this is where we use the digital base of the system. Why we migrate from analog to digital? There are actually many reasons. One reason is because of the noise, or the noise issue. And then 10 years later, in year 2000, 3G was introduced. So basically, for 3G, basically it can go up to 2 megabit per second. And 10 years later, in 2010, 4G was introduced. So basically, for 4G, it can go up to 1 gigabit per second. And 10 years later, in year 2020, 5G has been introduced. So basically, for 5G, it can go up to 10 gigabit per second. So you can see it's actually 10 times better internet speed compared to the 4G. I'm not so sure about the 5G in Indonesia, but in Malaysia, whenever we have our 5G phone, and in certain areas, especially in the big city, we are able to apply or to use this 5G network. And in 2010, 6G will be introduced. And basically for 6G, so basically we are talking about 10 times internet speed better compared to the 5G. And in terms of the latency, we are talking about microseconds of the latency. So in terms of delay, so very small in terms of the delay or latency. And we are also talking about high quality of the connectivity. What do you call that? I would say almost everywhere. So this is actually the objective, of the 6G. Okay, so just now I did mention about the technology evolutions, where you can see 1G, 2G, 3G up until 6G. There will be evolutions every 10 years. But when we are talking about creations for the new values for market, so basically it will occur every 20 years instead of 10 years. So the first wave of new value for markets, they call it as the first wave. So basically the objective of this first wave is actually to disseminate of mobile phones. So basically you can see currently, even our grandparents are having their handphone. So basically everyone should have the mobile phone. So this is actually their first wave. And the second wave that occur between 2000 and 2010, basically the second wave, the objective is actually for mobile multimedia. So basically from here you can see there are a lot of apps or videos that have been introduced. So for example, currently we use WhatsApp, YouTube, and etc. So this is actually where the second wave of the creating for the new value for market. And the third wave will occur between 2020 and 2030. So basically for this third wave, the objective is actually for new business value, and it will be concentrated on human and society. So this is actually the third wave that had occurred and will occur from now until 2030. So before I go much further, so basically over here I would like to explain about the comparison between conventionals and the cellular. Because just now I did mention about the one and only tower. This is what we call as the conventional, and then the introduction of the cellular concept, where we have multiple cells within the area. So basically for the conventional mobile system, basically it used no frequency reuse concept. Whereas for the cellular radio system, it uses frequency reuse concept. So what is this frequency reuse concept? This is something that I will explain to you later on. And second one, it used before 1980s. Whereas for cellular radio, it used after 1980s. For the conventional, it has low capacity, high transmitted power, high in terms of the antenna height. Then of course the equipment is actually bulky. Whereas you can see for the cellular, it has high capacity, low transmitted power, low antenna height, as well as the hand portable. Meaning currently we are able to hold our phone, which is actually portable, hand portable. Okay, so next one I think we'll go to the what we call as a cellular network concept. So basically for this cellular network concept, basically it uses several carrier frequency. Why we can improve in terms of the capacity? It's because we can reuse the frequency that we already use. And the frequency used here, for example, let's say this is actually the cell that used the frequency. They say frequency A. Basically, it can also be used over here. So meaning, let's say we travel from here, they say we travel from UI to Jakarta Central. Basically, whenever we approach, some of the cell, basically some of the cell are using the same frequency. But of course, the name of the cell itself will be different. For example, here they call it as a UI1. Maybe once you travel a bit further, they call it as a UI2 or whatever. So that's why when we travel, we can see that the name of the base station is actually changed from one name to another, because they have handover. So basically, for this one, the cell size may vary from 100 meters up to 35. It depends whether it is actually in the urban area or suburban area. And in terms of the shape of the cell, basically it uses what we call as a hexagon kind of shape. Theoretically they call it as a hexagons. Okay, so basically some of the special working mode for the cellular network. The first one is actually hand-off. So I think I did mention to you about hand-off concept. Where whenever we travel from one cell, from one place to another, so basically it depends in terms of the in terms of the signal strength of these users. If they say the signal strength is actually smaller over here compared to the adjacent, so basically it will hand over, or we call it as a hand off. And the other special mode that I think is actually that has been applied for the cellular network is what we call as a roaming. So meaning if they say if they say I travel from Malaysia to Indonesia, basically we can use a special working mode we call it as a roaming. So we can continuing using the services even though we actually outside our countries. And the other concept in terms of the practical handover considerations or hand-off considerations is what we call as an umbrella cells. So just now I did mention to you, if they say we travel from one area to another, basically they will be hand-off ataupun handover, hand-off from one cell to another. But the problem is actually in terms of speed. The speed of the moving object will be different. For example, let's say we actually pedestrian, the speed will be slower. But let's say we are talking about vehicles, and even currently, Indonesia, you have a high-speed train that travel from Jakarta to Bandung, right? Basically, the speed is actually very high. So if they say we have very small cell, which is handover from one side to another, then it will create stress, to the system. So that's why we have what we call as umbrella cells, where the area is actually divided into small cell as well as the big cell. So a large cell is actually for high-speed traffic, whereas the small cell is actually for low-speed traffic, for example, like pedestrian and etc. So with that, basically, whenever we have like vehicles, train, or high-speed train, they can use this large cell, So large cell, and this one will be another large cell. So basically, handover will not be very frequent, Alright, so this is actually the frequency reuse concept. Yeah, I'm not sure whether you have heard about this or not. If yes, then we'll be okay. So basically for this frequency reuse concept, basically users in different geographical area will be able to simultaneously use the same frequency. Yeah. So from here you can see, this is actually a cell, and this is actually this is actually this is a cell. Yeah, all right. So from here you can see that this cell, A and A, basically they're actually using the same frequency. The same thing goes here. This is B and B. So in B cell and B cell here, they actually use the same frequency. This is what they call as a frequency reuse concept. Right? So basically with that, then I think because in terms of spectrum, we have a very limited spectrum, right? So that's why whenever we have this frequency reuse, basically it will be able to increase in terms of the capacity as well as what we call that, improve in terms of the spectrum efficiency. Yeah. So basically from here, you can see that as what we had discussed just now, right? Cell with the same letter, they will use the same cell set of the frequency. Whereas this is they call it as a cluster. A cluster is actually a set of cells. This is they call it as a cluster. So meaning this is one cluster, this is another cluster, and this is actually another cluster. So basically with this, with this example, we can see that for the cluster, the cluster size is actually equal to 7. Meaning this is 1, 2, 3, 4, 5, 6, 7. So one cluster consists of the 7 cells. But it depends. It can be more than 7 cells per cluster. It depends. It depends. All right. So basically, from what we have learned, basically we should be able to use this frequency reuse concept, in order to improve in terms of the capacity, as well as in terms of spectrum efficiency. But the problem is actually, whenever we use this frequency reuse concept, we have to make sure that the cell here is actually not too far away and not to be what do you call that, close, too close and not to be too far. For example, let's say you are higher as capacity planning. So you should be able to make sure that design the cell to be not too close and not too far away. Because if they say it is actually too close, it can what do you call that? It can cause interference. But if they say it's actually too far away, then in terms of the efficiency will not be very efficient. All right. So we have we have to make sure that they are actually not too far away, not too close, too close enough. All right. Now, if they say we are talking about the frequency reuse concept, so this is actually the conventionals, and this is actually the cellular concept. So from here, you can see, with the same area. So this is actually the same area. For the conventional, they have only one radio base station, RBS. But from here, by having this cluster and the cell, we can see that, for this cluster, they say one is actually 660 channels. But they say we have 7 of these cluster. 7 of these cell in the cluster. They basically, in terms of the capacity itself, we can improve up until 4,620. And if they say in the same area, we have 7 cluster. So basically 4,620 for one cluster can be multiplied with 7. So from there you can see that in terms of the channels, number of channels can be improved significantly. So this is actually how it works. Okay, so in order to design of cluster size, or we call it as n, so basically it depends on this formula where n equal to I squared plus ij, I times j plus j squared. So it depends on I and j, where I and j, they are actually non-negative integer, meaning they can be 1, 2, 3, and etc. They are not negative. They are non-negative integer. So for example, in this case, they say we are talking about I equal to 3. I equal to 3 and j equal to 2. So from here we can see that what do you call that? Cluster size n is actually equal to 19. Yeah, so from here you can see that, yeah, when I equal to 3, j equal to 2, so we have 19 cells in the cluster. Yeah, so in order for us to locate, yeah, the co-channel meaning cell that using the same channel. So basically we can use this step, yeah. So this is actually the step on how we can do that, yeah. Okay, so basically we can start from a reference cell. So this is actually, let's say, a reference cell. Yeah. So how can we locate this A, right? Okay. So we have start from a reference cell. So this is the reference cell. Then we have to move I cell along any change of the hexagons. For example, let's say I equal to 3. So you will move 3. Yeah. So this is actually 1, 2, and 3. Yeah. For I equal to 3. And then after that, we need to turn 60 degrees counterclockwise. So let's say here, yeah, we have to turn 60 degrees counterclockwise. So from here, turn 60 degrees. So since j equal to 2, it will be 1 and 2. So this is actually where the location of the co-channel for E. Yeah. So let's say we take, yeah, for this one, for this side as well. All right. That one just now we calculate for that side. Yeah. Let's say we're talking about the opposite side. So I equal to 3. So it will be 1, 2, and 3. Yeah. Then turn 60 degrees counterclockwise. So turn 60 degrees counterclockwise. So we'll be here. So j equal to 2 will be j equal to 2, right? So 1 and 2. So this is where we can locate the co-channels for A, for this side. So the same thing goes with the other side as well. So this is how we can locate the co-channels. So the same thing, let's say we're talking about B, C, D, and etc. So it will be using the same concepts, yeah, right? So this table, it illustrates, yeah, the column and the row, yeah. So from here in the column we are talking about cluster size, which is N, yeah, and co-channel reuse ratio, which is Q, yeah. And for the row, it shows about I and J value, yeah. So just now, let's see, we are talking about, over here, we are talking about I equal to 1 and J equal to 1. Yeah, I equal to 1, J equal to 1. So cluster size N, by using that equation that we used just now, yeah, which is N equal to I squared plus IJ plus J squared, right? So basically from here, we can see that the cluster size is actually equal to 3. Yeah, the same thing goes, let's say, I equal to 1 and J equal to 3. So N, let's say using the equations, we can get, which is equal to 13, right? So this is actually how we can calculate the cluster size. And in terms of the reuse ratio, which is Q, yeah, by using these equations here, right? Okay, all right, so basically from here we can see, yeah, in terms of the co-channel reuse ratio, D over R, which is Q equal to D over R, and as what I did mention just now, yeah, the small value of Q, when Q equal to, which is reduced, yeah, then D will also be reduced, yeah, so basically whenever D is actually reduced, yeah, so it will provide larger capacity. Yeah, because whenever Q equal reduced, Q is actually reduced, the overall also will be reduced. Then basically it will provide large capacity. But whenever we increase Q is actually increased. Yeah, Q is increased, the overall will be increased. Basically, it can improve in terms of the transmission quality. Yeah, because due to the small level of co-channel interference. Yeah, because whenever distance between center of co-channel is actually increased, so interference also will also be reduced. Yeah, so that's why we have to make sure that we have the optimum Q value. Yeah, okay. Okay, just now I think I did mention about the theory, yeah, in terms of the cells, how it looks like, yeah. So basically, in terms of the shape, yeah, it can be in terms of square, triangle, as well as hexagons, yeah. But hexagon has been chosen, yeah, because in terms of design, it is much more simpler to design, yeah, for the cell. Yeah, compared to a rectangular or a triangle. Yeah, so that's why. Yeah, let's say you read in terms of the from the book or something. Yeah, so basically we use hexagon cell shape. Yeah, instead of other shape. Okay. Alright, so basically this is actually how the cell looks like, or the tower, how it looks like. Yeah, so from here you can see we have the directional antenna, we also have the sectorized antenna. Yeah, so this is actually the common radio base station that we usually see. Okay. All right, in terms of the cell size, basically we can divide it into different types. For example, we are talking about macro cells. Yeah. For the suburban area, yeah, we are talking about micro cells, yeah, for the urban area, as well as the pico cells, for very small area, yeah. So this is actually the cell size that we are usually referring to, yeah. Or let's say we are talking about global, usually we use satellite for the global. Yeah, I think just now, I think a few weeks ago, I think the Asian World Cup has just finished, yeah. So usually we use the live telecast, right? So basically we use the satellite, yeah. Okay, so for the macro cell, basically usually used for outdoor, and used for rural, suburban as well as urban area, yeah. So basically used for medium traffic density, yeah. And in terms of the radius, yeah, of the cell, yeah, the radius is around 10 to 35 kilometers, yeah. So basically this is macro cell. Second one is actually the micro cells, yeah, for outdoor and indoor, and it used for high traffic density. Yeah, and for the pico cells, basically for the indoor environment, yeah, usually it's used for high traffic density. Yeah, so this is actually in terms of the cell size. Yeah. So in terms of the type of cell site, basically it can divide it into two. The first one we call it as an omni cell site. Yeah, and the second one is what we call as a sectorized cell site. Yeah, and for the omni cell site, basically we use omnidirectional antenna. Usually for the suburban area, where the population is actually not very high. Yeah, so basically we use omnidirectional antenna. Yeah, and for the sectorized cell site, basically they call it as a directional antenna. Yeah, directional antennas. So there are actually certain advantages of the sectorized cell site, or they call it as a directional antenna. So the first one is actually in terms of the power, where the power use is actually much more lesser compared to the omnidirectional. Yeah, in terms of interference, it has a better interference. Yeah, and in terms of capacity, it has a good in terms of the capacity as well. Yeah. And this is actually how the sectorized cell site looks like. Yeah? So for example, they say we are talking about the cell. Yeah. So basically the cell itself can be divided into sectorized. Yeah. This one here, we're talking about 120 degrees sectorized, meaning, yeah, each of the sector, yeah, it has own sectorized antenna. So it covers about 120 degrees. Yeah, each of these angle. Yeah, and for this one is actually for 60 degree sectorized. Yeah, so basically it consists of 6 sector. Yeah, each of sector. Yeah, the beam width, yeah, is actually 60 degree. Yeah. All right. Next one is actually in terms of the interference in cellular radio system. Yeah. So basically we are talking about 2 types of interference. Yeah, because whenever we are designing our system, right, and so we also have to make sure the interference is actually less. Yeah. So in terms of interference in cellular radio system, basically it consists of 2 types of interference. The first one is adjacent channel interference, and second one is what we call as a co-channel interference. Okay. So for co-channel, I think I did mention to you just now, where the cell that use the same frequency. Yeah, so this is what we call as a co-channel interference. Whereas for the adjacent channel interference, is actually where interference between channels which are adjacent, all right, next to another. Yeah, and I think this figure illustrates about the adjacent channel interference. So from here you can see that, yeah, we have channel 1 and channel 2. So you can see here from the upper side of channel 1, it interfere with the channel 2. Yeah, they interfere with the somewhere which is here. Yeah, the end part and the initial part of this channel that actually interfere. So this is something that we need to avoid. Yeah. So in order to avoid it, yeah, basically we have to spread out this channel. Yeah, we have to spread out. Yeah. So how to do that? Yeah. So how to do that? Yeah. So basically one of the techniques that we use is actually by do not allocate channels for a given cell from a continuous band frequency. Meaning, they say we are talking about channels 1, 2, 3, and 4. They're actually continuous, right? And so instead of 1, 2, 3, 4, 5, channel 1, 2, 3, 4, 5, then basically we use channel 1, 8, 15, and etc. So how does it look like? I think this figure here shows an example of the GSM system for 7 cells per cluster. So from here you can see that it consists of 7 cells. And in terms of channels here, you can see here channels, cell number 1, you use channel 1, 8, 15, and 2. Whereas channel 2, cell number 2, you will use channel 2, 9, 16, and etc. And for cell number 3, you use channel 3, 10, and something. And from here, you can see that, channel 5, it has its respective frequency. And for example, here we're talking about 8890.1. So basically from here, the channel 8, the frequency is 891.5. So you can see that they actually split out. So basically, it can avoid in terms of the adjacent channel interference. Okay, so this is actually how this looks like when we are talking about the cell. You can see this is actually 7 cell per cluster. So each of the cell, they actually what do you call that? They actually spread out in terms of the channels that it is used. And from here, we are talking about sectorized. So basically, when we're talking about sectorized, we can divide it into 3 different sectors or 6 different sectors. So this example where we use 3 different sectors. For example, let's say this cell, we have sector 1A, 1B, and 1C. So in order to avoid what I call the adjacent channel interference, basically we can divide it into this sequence. So we have 1A, where the channel is actually channel 1, 22, and 43. So 1B use channel 8, 29, and 50, and etc. So from here we can see that by having these kind of distributions, so basically we can avoid in terms of the interference. This is another what do you call that example of the how we can design sectorized cells and avoid the adjacent channel interference. Alright, so this is some example of GSM spectrum in Malaysia for 900 GSM 900. I think I can skip this. Okay, so this is something about the co-channel interference. So basically, I think I have explained to you. I think we can skip this. So the other concept is actually about the cell splitting. So basically, when we are talking about cellular concept, so basically cell splitting is also very, very important because by having this cell splitting, we will be able to increase the traffic demand or the traffic capacity. So basically, by having this cell splitting, basically we divide a cell into a smaller cell. So from here, it shows this area, where it has different cell size, as well as different cluster, cluster size as well as cell size. So this is some of the what I call typical cellular radio cell plan in one of the area. So in terms of coverage, as I did mention, basically theoretically we use the hexagon shape, but in reality basically the shape will not be hexagons, and of course this is actually due to many factors. For example, due to the transmitted power, due to the terrain, some area might be hilly, some area might be valley, and etc. Alright, so basically factors that influence coverage will be transmitted power, height of the transmitter, terrain, as well as the customer expectation. Because some customers, the expectation is actually quite high. Some customers, the expectation is actually not that high, So what cause in terms of low coverage? Basically, there will be some areas that might not be fully coverage by this network, and usually this is actually like behind the tall building, valley, and etc. Alright, in terms of building coverage, basically as we understand, area that has wooden wall is better in terms of the coverage compared to like hall which has a very thick wall. cement wall, yeah, and number of windows also play a very important role, yeah. More windows means better coverage, yeah. Okay. All right. So maybe next one, I think maybe I'm going to take a few more minutes, yeah, to explain about the large scale path loss models, yeah. Okay. So when we're talking about propagation, basically we are talking about communicating between users and the base stations. Yeah, so they will be like downlink and uplink communications. Yeah. Then I think in terms of the propagation models, basically we can divide the models into two. One is what we call as a large scale models, and the second one is what we call as a small scales models. Yeah. So basically, for large-scale model, basically it used to predict the receive signal level, and because in order for us to calculate the power received, yeah. So basically, we can use this large-scale model. Yeah, basically we are able to understand the variations, yeah, in term due to the path loss as well as due to the shadowing, yeah. And then from the large-scale model, basically we understand, the further that we move away from the cell or from the radio base stations, yeah, the weaker signal that you have, yeah. So let's say we look from here. This is actually an illustrations how we can compare between large scale and small scales, yeah. So from here, yeah, so we actually talking about this radio base station here that transmit the signal. So let's say we are talking about different location, location A, B, C, and D, yeah. Yeah. And let's say we draw, yeah, a figure where Y analysis is actually the receive power, and X analysis is actually the positions, yeah, position A, B, C, and D. So from here, when we're talking about large-scale propagation, yeah, let's say we're talking about position of A, yeah, so this is actually the receive power that will be received, yeah. Whenever we're actually moving from A to B, and this is actually where we have, they call it as a shadowing area, then of course the signal, receive signal level will be reduced. Okay? So we will reduce, yeah. And whenever we move to C, yeah, of course it's still reduced because it is still within the area of the shadowing, yeah. But whenever we move to D, then of course, yeah, in terms of the receive signal level will be increased. Sorry, this is typo, should be D. Yeah, so the blue one here is actually is for large scale model. So we are able to calculate the receive power. Yeah, but the one which is actually with this blue shape, yeah, is actually what we call as small scale propagation, and then this is actually due to the fading. So that's why it looks like this. Yeah, instead of just a normal what we call that shape, yeah, of what we have for this blue side here. Okay, all right. So when we're talking about large scale, about the free space propagation models, basically it is actually based on the free space equations. The power received is actually equal to power. Let's say we're talking about this transmission. This is transmitter and receiver. The power received here is actually equal to power transmit plus gain transmit of this antenna, yeah, plus gain receive, yeah, as well as on the distance here, yeah. So basically it depends on the gain transmit, gain receive, power transmit, as well as the free space loss, which is depends on distance as well in terms of the frequency, yeah. So this is something that we usually use, yeah. Then effect of the environment. So basically whenever we transmitted some signal, so there will be effect, yeah, due to the environment. And the three main effect, yeah, is actually related to the refraction as well as the diffractions. So what is actually reflection? So basically reflection is actually whenever the electromagnetic signals, yeah, it impinge, yeah, on a large object, basically it will change in the directions of the wave itself. Yeah. For example, let's say we transmit a signal from here to here, right? So whenever it pinch to the last area over here, so it will be reflected. Yeah. So effect of this reflected, yeah, basically it can create extra signal, yeah, but with delay, yeah, but with reduced power attenuations and also with delay. Yeah, so basically it will cause a delay, yeah, as well as in terms of what we call that extra copies of signal with power attenuations, yeah. So this is actually effect of the reflections, yeah. And the other one is actually they call as diffractions. Yeah, diffractions occur when EM signals, they actually diffracted over the top or at the edge of the sharp edge, of the objects. So basically from here we can see that whenever this diffraction occur, so basically you can see that even though we have a very big mountain over here, the signal can also still be received at the back of the big obstructions. But of course there will be some area that will not be able to receive a signal, and this is what we call as a shadow area. But some area can still be received even though the transmitter is from here. So this is actually the effect of these diffractions. And diffraction, it can it has three different categories. Whenever the transmitter and receiver, the edge here is actually much more higher compared to transmitter and receiver. The second category is actually whenever we have the transmitter and receiver, the edge is actually on the same level. The third one is actually whenever the transmitter and receiver is actually on the top of this sharp edge. So this is actually the diffraction may occur. Of course. And the third one is on the scattering. Scattering occur when EM signal, it impinge on small object. What actually the small object? For example, let's say we are talking about the foliage, daun-daun, foliage, street light, lamppost, small any small things. This is what we call as a scattering. And the effect is actually, there will be some effect. For example, the scatter field, it can increase the signal strength of the signal at the receiver. It depends. Okay. So basically, the scattering, it can occur. Whenever the EM is actually impinged into the small object. All right. So basically, in general, what we can see that for the transmitted signal, basically the signal can be reflected, can be refracted, can also be scattered. So whatever the signal that we receive is actually the resultant of the effect actually. All right. In terms of the Pavlov model, basically we can divide it into analytical models, empirical model, as well as composite models. Analytical model is actually based on the analyzing of EM models. Example is actually free space model. Two-ray model. This is they call as an analytical model. And in terms of the empirical models for this cellular network, basically it obtained from measurement. And the composite is actually a combination of analytical and the empirical model. Okay. Due to the time constraint, I just show you one measurement models. This is actually a very famous model. Whenever you read the book, they call it a Okumura model. So this is actually designed by a guy named Okumura, and he did the measurement around Tokyo area. Basically in this model, basically he determined the free space path loss. And in addition to that, he also adding and subtracting some of the correction factors. And basically this model used for 150 to 1920 megahertz. Basically this is for GSM. Then the distance, it can go up to 100 kilometers. And base antenna height from 30 to 1000 meters. And it can also be used for urban and suburban area. So this is actually the models. Right. So this is actually how the equation looks like for this model. I think I'm not going to explain more details about this. All right, and this is actually some of the correction factors. From these figures. For the median attenuations. For the G area. Into other area. All right. Okay, so basically, last but not least, basically I would like to share with you one of the grants that currently I'm heading in. They call it as the Asian Evo project. And I believe UI also, Prof. Fitri also can apply for this grant actually. So basically for this project, actually we try to address issue in terms of the public transportations. So basically. Maybe not in Indonesia, but maybe some other part of the different countries. So basically, we are facing in terms of the overcrowding, as well as inconsistent of travel frequency. Yeah, so basically the bus which is traveling might not be consistent, so people have to wait for a very long time, yeah, in order to wait for the bus lah. Yeah, but when I came over here in the morning by using the bus, and I think the bus over here is actually very good. The yellow bus. I don't know what is the name of the bus, but the bus is actually very good. I think it has its own what do you call that, mobile apps, I think. Yeah. Okay. So here no problem, but maybe some other places. Okay. So basically in this project, basically we try to address the issue of the public transportation system. Of course, with the introductions of the GPS, yeah, we are able to locate GPS inside each of the bus for us to do tracking. Okay, but in Malaysia, yeah, not all the bus company are able or are capable to purchase the GPS or the router because of the cost. And for example, the cost of one router, the system, maybe about 2,000 ringgit. I'm not so sure about in terms of rupiah, and because rupiah you have so many zeros, I also get confused with the zero. Okay, but ringgit, 2,000 ringgit. Yeah, so not all the bus company are able, rich enough to buy it. Yeah, because then I think that's why we propose this system. Okay. So basically, this project, yeah, it consists of different members from different universities. Yeah, the head is actually me myself from UTM. So over here we also have members from University of Glasgow, Singapore. Yeah, we also have the members from Universiti Teknologi Brunei, from Brunei. We also have members from Universitas Brawijaya, I think somewhere in Malang. Yeah, I think Jawa Timur, yeah, Jawa Timur, Malang, yeah, and USM in Malaysia as well as Utah. So basically we have 6 universities which is running this program. Yeah, so basically what's actually this project is all about. Yeah, so basically in this project, what we are doing is actually we install a Raspberry Pi in some of the bus stop. Yeah, so whenever bus, yeah, pass through the bus stop, yeah, then the system will be able to detect the bus. Yeah, in order to do that, basically we have what we call as a ST mode. Yeah, ST mode we install inside this bus. This is Raspberry Pi. Basically, we use the Bluetooth technique. Yeah, so whenever the bus pass through over here, so it will be able to detect it. Yeah, then from there, then we send it to the cloud for deep learning, yeah, machine learning. Yeah, then after the process and etc., it will be transferred back to the users. So from there, you will be able to, the users will be able to know the ETA, yeah, for that particular bus. Yeah, and the good things about this one is actually the cost of this is actually about 100 ringgit. I would say 10 times cheaper, yeah, compared to what we have by using the GPS. Okay. Right, so this is actually the testbed that we have in Johor. We have 2 testbeds, one in Johor, one is actually in Malang. So in Johor, we have these 2 routes. They call it as a route P211 and route P411. Route P211 is actually all the way from Skudai area, which is very close to our university area. So basically, the bus is actually going from here, go to inside our universities, going out, then from there, it will go to the city center. And the distance here is about 20 kilometers away. Of course, we will not install in each of the bus stop, yeah, because it will be very, very difficult. So we just install in some of the bus stop. And the other one is actually route P411. Yeah, basically it has like 31 bus stop, but we do not install all. Yeah, basically from here, yeah, the distance here is actually about 30 kilometers away, about 35 kilometers away. Yeah, so whenever the bus pass through the bus stop, so it will be able to detect, then send to the cloud. Then from there, then I think we use some machine learning. Then I think it will be able to what do you call it, to detect it. Yeah. So basically, of course, yeah, the project is not done alone by my side. Actually, we have like UB. What do you call that? We have University of Glasgow, Singapore, yeah, and other universities. Yeah, they're actually working on this machine learning because we are not from computer science. We are from the electric engineering. Yeah. Okay. So All right, and this is actually the testbed in Malang, and basically the testbed in Malang, it is actually a bit smaller compared to what we have because because I think in Malang they do not have a public bus. I'm not so sure, but they said that they did not have public bus, but they use a school bus. So basically for the school bus, they have installed 8 Raspberry Pi units along the route. And this is actually how it looks like. And the good things over here compared to what we have in Malaysia, basically over here in Malang, basically they have 24/7 electricity, whereas in Johor we do not have that. Because we install on the lamppost, so the lamppost, it has only electricity from 7 p.m. until 7 in the morning, so only 12 hours. So basically, we need the battery in order to charge and discharge purpose. Okay. All right. So this is actually where we install that beacon. So if you can see from here, this is the beacon. Very small. The shape of a mouse. Very small. Right? That's why the price is 10 times. What do you call that? Cheaper, 10 times or more cheaper compared to what we have in terms of these GPS actually. Okay. All right. So I think thank you with that. So I think thank you for your patience. Maybe a bit longer my presentation, but I would like to thank you. All right. So thank you. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera.
Thank you. Okay, let's give a big applause again for Professor Sharul Kamal. Okay, thank you. Baik, nanti setelah presenter kedua akan ada sesi tanya jawab. Jadi buat teman-teman yang di sini, kalau ada pertanyaan mohon disimpan dulu, dan untuk teman-teman di Zoom boleh ditulis di kolom komentar. Oke, untuk sebelum kita mulai presentasi kedua, saya akan bacakan dulu CV dari Profesor Norhudah Seman. Norhudah Seman received Bachelor of Engineering from Universiti Teknologi Malaysia in 2003 and Master of Engineering in Radio Frequency and Microwave Communication from the University of Queensland, Australia in 2005. She obtained her PhD degree in Electrical Engineering from the University of Queensland in 2010. In 2003, she was an engineer at Motorola Teknologi P.Eng, where she was involved with the RF and microwave components design and testing. She was Director of Communication Engineering from July 2018 to June 2021 and Acting Director of Communication Engineering from July 2021 to June 2022 at School of Electrical Engineering, Faculty of Engineering, UTM. Currently, she is Associate Professor in Faculty of Electrical Engineering and Director of High Center of Excellence of Wireless Communication Center. Her research interests concern the design of microwave millimeter wave device, the effect of electromagnetic field radiation, including specific absorption rate or SAR, and power density and wireless communication. Without further ado,
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, selamat sejahtera. Okay. So you have learned actually about the cellular concept just now. So I hope you can actually understand. Okay. So how is it? Good? Okay. So let's go to antenna now. This is actually the same slide that I'm been teaching my master students. Okay. So probably a little bit difficult, but I think that you can relate with what Prof. Sharul and what been actually implemented in current 5G. So we implemented antenna array and we call some sorts of smart antenna. So antenna not smart, but we give some intelligence to the antenna to become smart. Okay. Okay, so let's go to the what is antenna arrays. So antenna arrays is actually consists of multiple elements of the antenna. So one antenna, it can be like a rectangular patch. Have you seen like antenna, the square ones? Or the most actually common in residential area, Yagi Uda. Yagi Uda is the televisions antenna, aerial. Okay, so you see that's a lot of wire, right? Okay, it can be looks like fish bones. So it's actually dipole, array of dipole. So that's antenna array. Okay, so one element is just like one wire or cable, but being placed about 0.5 lambda, a distance between the antenna. So we have a few of element. So that's actually antenna array. So it's usually that we have the identical antenna placed at certain distance, so it become an array. Okay. So this antenna array is actually capable to what we call is to match the radiation pattern. So we actually add. Okay, so mathematically, let's say one element have gain of 1, and then we have 5 elements, we can add 1 to 1, 1. Okay, so mathematically, okay, when we always assume when we do mathematical, one antenna has 1 gain, so we can add, but practically not like that. But the idea is to add the radiation pattern, so we can actually focus the strength of the beam towards certain area. Okay. So then what antenna array can do is to actually change the radiation pattern. So how to change? So antenna not smart, right? So when it's radiate, it radiate at certain directions. So how to change that to become smart? So what we do is we control the phase and the amplitude that we feed to the antenna. So when we actually controlling the phase, we can change the directions of the radiation pattern. So then the antenna become smart. Okay. So by this antenna array, so when we have more antenna, so we match the radiation pattern, so the gains become increase. So when the gain increase, okay, and then we also able to increase the capacity, transmission capacity. Okay. However, okay, with more antenna, it become more complex and more costly. Okay. Okay, so in an antenna array, so what we controls, there's a 5 actually factors that we can control. So it's configurations, how we place the antenna. Okay, so how we place it, one element to another. Okay, and then the distance between these single elements of the antenna, and then the excitation amplitude. Okay, and the phase also. Okay, and then the relative patterns of the individual elements. So the individual elements have certain shape of radiation pattern. So based on that, also when we add the strengths of the radiation patterns, so from the single element it will determine what the radiation patterns that we will obtain. Okay, when we form an array. Okay, so this is a 2-element array. So what we did, okay, I'm sorry. I think that because of the, okay, the formats, different format. So it's supposed to be, okay, rotate to the left, okay. But what we have here is 2 dipole actually. There's 2 dipole. Okay, 2 dipole, okay, placed at a distance of d. Okay, so when we have a 2 dipole at distance of d, the strength we can actually, okay, get the strength at certain distance from these 2 of the array. Okay, so array of dipole. So So there's a calculations to calculate, okay, the strengths of the signals, okay, the radiation patterns from these two dipole at any distance from the array. Okay? Okay. So what we did, okay, so we actually can estimate or the total radiated electric fields by these two elements is the summations from each of the elements. Okay? So the total here, okay, see that. Total field radiated by the two elements is, okay, E1 plus E2. So this is from the first element, this is from the second element. Okay, so this is the equations, okay, to describe, okay, the radiated total field, electric field from the antenna. Okay. Okay. So there's a few, okay, parameter that we can use to actually control the beam. So here, okay, so we have this beta. So this beta is actually difference in phase excitations. Okay, so the difference phase between one element to another. So that's we use to control the directions of the beam. Okay, so when you change that, you can actually change the directions. Okay, okay, so this actually below here. So what we did, okay, so this is, okay, the parameter R1, R2. So coming from the first element, distance from second elements. So the theta is the directions, okay, of the beam from the, okay, antenna. Okay, okay, let's move to the next one. Okay, so this one, okay, so the total, actually the totals of the radiated field from the array of these two elements, okay, so based on the previous equation, we can simplify that to, okay, so what we have here, so the field from the single element multiply with the array factor. Okay, so the array factor, so when we know, okay, from single elements and we can calculate the array factor, so when we multiply the number of elements, so we can estimate actually what is the the radiated field from the antenna array. Okay, so this is the, okay, the general equations. The total electric fields is equal to element factor, okay, from the single element times the antenna array. So what we know is actually with one elements, and then we can actually have the antenna array factor. So calculate that, we can estimate the radiated fields. Okay. Okay, so what we have here is to show that when we have more antenna elements, so n element, so the array factor is actually summations from one element to another with the additions of this, okay, beta, theta, k, d. K is the wave number, d is the distance between the elements. Okay, so from the first elements, second, third, and so on until n elements. Okay. Okay, so this is the general equations for the array factor. Okay, so we have what we have here. Array factor is the totals of, okay, the summations of from the first element n equal to 1 to n element, so the capitals, okay, e power of j n minus 1 phi, where phi is actually defined by kd. K is the wave number, okay, d is the distance between element, this theta is the directions, and beta is the phase difference between the elements. Okay, so now we go on the how we want to calculate the array factor from the configurations of the antenna. So this is the most common, planar array, okay, and the linear array. So just now is the linear array. So in terms of the planar array, which being actually used, okay, quite popular now, okay, to wish to achieve let's say massive MIMO or MIMO, okay. So the forms is in the x and y axis, okay. So what we have here, okay, so what we have here, okay, so m elements, okay, we place along the x axis, so this one, okay, x, okay. So by this is actually quite similar to the linear array, this one, and then we're going to add by the columns, okay, to become planar array, okay. So if m elements we place along the x-axis, as shown as this, the array factor can be given by these equations, okay. So what we have here, okay, is quite similar to linear array. So we have the distance, okay, we have the phase and the excitations, okay. Now let's go to the next one, okay. Then we're going to add more, okay, antenna, okay, so by the columns, okay, so we have more, actually columns of antenna array, okay. So if n such array placed next to each other, so we have m here and n across the end, so we have m times n, okay, array, okay. Then what we did is to have the distance dy, because it's actually at y directions, okay, and we have same, so we have a phase difference between the elements, okay. So if we put the phase 0, is actually it will not change the directions of the phase, okay. So the array factor become more complex now because we have more antenna, okay, so it become planar now. And then from here we can actually separate the array factor between, okay, the sx, okay, m, okay, reference to this, and then syn, okay. So but it's actually quite similar, okay. It just this m reference to this number, and then this n referring to this, okay. Then so we have this kd, so k similar to the one, k wave number, 2 pi over beta, and then d is the distance across this x-axis, dy is the distance between the elements across the y-axis, okay, okay. And then we have, so this theta, the directions, okay, we have the phi and the phase difference, okay. So usually what we do to controls is to give different phase to this, each of these antenna elements, okay. Okay, so how we going to fit this array? So there's actually a numbers of way to fit the array, okay. So this is, for example, the first one is the series fits, okay. So the next one, this one is corporate fit. So the corporate fits is actually using a feeder, something like a common power divider. Okay, it's going to divide the signals equally, okay, to the array. Okay, so by having this one, okay, this way, so for the series fits, okay, so the performance or the characteristics of this actually is quite limited, because the array will actually have fixed beam. Why? Because we only have one fit to the array. Okay, there's no change in terms of phase difference between the elements, so it's still similar, right? Okay, for this one, you can use that. You can increase the gain, but it has same fits. Okay, so any changes in one of the elements or the feeds line will affect, because the feeder is only one. Okay. And then it's important to take into account of the mature coupling, because it's been connected. Okay, let's see this one. Okay, this one is quite common feeder to the antenna array. Okay, so you can use there's no limits in terms of the number, but when you use this one, probably it becomes more complex, because you need to have a lot of this branch, right? Okay, it's look like branch, but we can actually control. Okay, so when I teach the class, usually that I say, so when the student doing the simulations, what I usually that tells them, okay, to change the length. Okay, just change. You have different length between one element to another. It means that, let's say this one use 5 millimeter, the next one you use 20 millimeter. You change. By changing the lengths, also will give different phase. Okay, that's quite simple to do to the antenna array. Okay, so when you change the phase, okay, the length of the transmission line feeding the antenna, you change the phase. You will see when you simulate, okay, the radiation pattern, you will see the direction will be changed. Okay, so you can play around with that. That's quite simple things to do when you actually learning, okay, about the antenna array to relate with the complex, that's mathematical equations, right? It look complex, but we need to do, what we need to do is just controlling actually the phase to the antenna to control the directions of the beam. Okay, so this is just example. So there's a lot of things that we can do to the feeds. Okay, so just to want to show the change in terms of the impedance. Okay, so this is based on the feeder, this one. So it based on the power divider. It's quite simple actually to design. Okay, so this is examples of the antenna array. Okay, even though what you learned just now is linear array and also planar array. Okay, that's the most common. But when you place the element, you can place it as actually, it depends on you. You can do a lot of things with that. Okay. Okay, so that's why sometimes like probably the array is not like conventional linear, and the distance also. The distance between the elements, you actually can have unequal distance. Okay, so there's no strict rules in designing antenna, also the antenna array. Okay, so let's go to the smart antenna. So we have learned through the array factor. So when we controlling, okay, especially the phase, the directions of the beam will change. So that's how actually the antenna becomes smart, because we want to change the strength, we want to change its directions. Okay, usually, okay, what we do, okay, to combine, okay, the basics ideas using the phase difference between the antenna elements with the digital signal processing. So we add some things, okay, to control, to make sure that our passive antenna become smart. Okay, so you just learned about the cell setterings. Okay, so when setterings mean the beams when it's covered 60 or 120, so it's static. But in 5G, the beam not static. It's moving. So how to move the beam? You need to change the phase. So that's what actually 5G implements. So the beam moving following the user. Okay. So let's take a look at two basics types of smart antenna. So I will covering switch beam and additive array. Okay, so switch beam, a static beam. Okay, but for the additive array is actually you can control. Okay, so let's take a look. Okay, so switch beam. Switch beams, okay, so just now what you learned, okay, just now what you learned, we have a sector, right, sector. Okay, this is total 360 and one sector is 120 degree. Okay, 120 degree. So for the switch beam, we have a static beam. Static beam, okay, with the array, we can have a lots of multiple beam. Okay, so when we have multiple beam, okay, smaller with the array, the beam becomes smaller, right? Okay, then we can divide. What we did is what we do here. Okay, for the sector 120 degree, we divide it with multiple of beam, smaller beam. Okay, smaller beams. Do you know why we need to use smaller beam? Gain. Okay, okay, high gains. Okay, when we have array, okay, you understand, when we add the gains, right? We add the gain 1 plus 1 plus 1. Okay, 1 plus 1 plus 1. So the gain become increase. Okay, but the size of the beam become smaller. Okay, so let's say we have 4 array. Okay, if we have 4 inputs to the antenna, and then we have 4 antenna, so we can create 4 beam. Okay, with changing the phase difference to the antenna. So we have, if we have more antenna, we have more beams. So that's the basic idea. Okay, so for example here. Okay, so we cover, so this 120 degree, for this, for example, we have 1, 2, 3, 4, 5, 6 beam. Okay, so switch beam system. Okay, so a system will choose actually. So when we have a user, so the system will choose one of the predetermined patterns, so the beam, to the user. Okay, so to enhance. So if the user located here, for example, this one, so the system will give this beam, okay, to the user. Okay, okay. So compared to the additive array, okay, so the additive array system, okay, this one, for this one, okay, so it will direct the main beam toward the user. So it change, okay, it will direct the beam towards the user. Okay, so the user will have slight dedicated, right? And then the signal strength high to that user. Okay, so this, for example, you can take a look at this speaker. Okay, so So, okay, user 1. Okay, so when we have user 1 here, okay, so we have this beam, okay, will be directed to this user 1, and the interferer will be given the null. Okay, it's not receive the signal. So that's difference between switch beam and adaptive array. Okay, so there's more comparisons, okay, between the switch beam systems and the adaptive array system. Okay, so when we have units actually moving throughout the cell, the switch beam system detect the signals strength, choose the beam to the user. Okay, and then if the user move, okay, what the system do is change the beam. Okay, so you move to the next one, so it give the next, so it's not moving the beam. Okay, so the beam is already there, so it just changed that slight hands over. Okay, okay, but for the adaptive array, okay, it can customize the appropriate radiation pattern to the individual user. Okay, okay, so the goals of this switch beam, okay, system to increase the gain according to the locations. The beam not change, so it give the predetermined beam to the user. Okay, and then, okay, so there's a disadvantage of this switch beam because the beam statics is there. Okay, it's not moving, so it's there. So, okay, so that user may not receive the best. Okay, it's not at the locations of the centers of the beam, so it will receive less strength. That can be actually become some disadvantage of this one. Okay, and then this switch beam also is not able to place the desired signals at maximums of the main loop. Okay, also it may not able to reject the interferer. The beam probably not supposed to actually send the signal to this unwanted user, but since it's the beam statics, okay, so it may actually not able to fully reject the interferer. So from these two disadvantages, we see that the adaptive array better than the switch beam. Okay, so the adaptive array system have the ability to control the radiation patterns. Okay, it can direct the radiation patterns to the desired user, and then reject the interferer. So it give the interferers null, so the interferers not receive signals. Okay. Okay. However, okay, adaptive array generally more digital processing required, so it needs intensive jitter signal processing. Okay, so it need also complete RF portions, okay, at the transmitter and the receiver, which actually becomes more costly and complex compared to the switch beam system. Okay. Okay, so this is comparisons between the switch beam systems and the adaptive array. So we see that, okay, what we have here for the switch beam, so the feeder to the antenna element called as beamforming network. So this beamforming network formed by only passive components. Okay, so you don't need to actually supply the power to the this component to operate. Okay, just need to control what the beamforming do, controlling the magnitude and phase towards the antenna. So it's, in comparisons, it's more simpler compared to the adaptive array system. So for the additive array system, what you can see here, okay, so we have the parts which we need down conversions to the basebands, and we also need to have analog to digital converter. Okay, so what we have here, down conversions is mostly mixers. Okay, and then we need to actually give some weight to the, okay, to each of these lines, okay, to the antenna. Okay, and then we have the algorithms. Okay, so we have more complex algorithm to control what the things that we need to control. For example, the amplitudes and the phase. So we need to have to give that informations. Okay, so we need to do lots of calculations. Okay, so okay, so what we do for this one is to controlling, okay, amplitude and phase excitations. Okay, so when we control the amplitude and phase, okay, so for the beamforming network we can control by using the passive components, coupler, power divider, the phase shifter. But for this one, it needs to control electronically, meaning you need to use the algorithm to do the calculations in controlling the amplitudes and the phase. Okay, so we need to give some weight. Okay, so what is the value that we need to give? So what is the phase? What is the amplitudes? Okay. Okay, so in terms of the switch beam, which more, even though we say that's additive array, better. Okay, but since it's more complex, it's more costly, it needs a lot of algorithm to control the amplitudes and the phase. Okay, at the front end, okay, we usually use the switch beam. So there's a multiple options in actually choosing the beamforming network. So this is some of the example. Okay, so we have Butter matrix, Rodman's lens, blast matrix, Nolan matrix. Okay, so there's options to choose. Okay, let's take a look what the difference between these four. Okay, so this is the first one is Butter matrix. So Butter matrix, okay, the most popular beamforming network that consists of couplers, phase shifters and crossovers. Okay, so what we have here, okay, so if you have learned about the coupler, so we have coupler, okay, this for coupler, crossover and phase shifter. Okay, so this is what we have here, 4 inputs and 4 outputs. So with 4 inputs, 4 this, okay, antenna. So what we have here is 4 beams. Okay, so okay, when we have the input from port 1, okay, port 1, so let's take a look what is the directions of the beam. Okay, beam 1, this one directed to plus 12 degree. Okay, when port 1 feed with the signal. Okay, so it means that when we change the port, we change the phase. When we change the phase, the directions of the beam will be changed. Right? Okay, so let's take a look at another example. Okay, let's take a look at port 3. So port 3, okay, so what is the directions of the port 3? When we feed the port 3, it will be directed to positive 50 degree. So So it's mean that. So when we change for this one, the button metric, when we change the input, we change the phase difference between the antenna. Okay, so we have actually changed the directions of the beam. So why we have 4 beams? Because we have this 4 input. Okay, 4 inputs. With this array, we have 4 beams. If you want more, you need more. Okay, so you need to have more inputs. Okay, and then if you want to have more gains, okay, so you can add more antenna. So, but usually for the barometric is designed based on it's like you need to design with 4 input, 4 outputs. That the most common. Okay, so let's take a look at the Romans length. So Romans length become actually popular because what we do with this Romans lens is actually controlling the aperture of the lens here. Okay, so this is the antenna. This is the antenna. 1, 2, 3, 4, 5 for this example, and then we have, let me check it. Sorry. So the antenna here 1, 2, 3, 4, 5, 6, 7. Okay, and then this is the beam ports. Okay, 1, 2, 3, 4, 5. So when we controlling the phase, you see that's the difference of the length with input to the antenna. It has different length. So the first antenna, second antenna, third antenna, fourth antenna, it has different length. So the phase will be different. Okay. So, but for this, okay. So, but with this Romans lens, okay, it needs to have these dummy ports. Okay. But in terms of the designs, is becomes popular because it need to control these apertures and the length here. Okay. So this is another example, blast matrix. So for blast matrix, so no restrictions in terms of the inputs and the output, but it needs to have the terminations. Okay, terminations here. We need to terminate the ports. Okay, with usually 50 ohm. So we have another one. This is the volumetric. So the volumetric actually based on barometrics and combination of barometrics and blast matrix. Okay, the good things, okay, with volumetric, it's also there's no restrictions in terms of the input ports and the output port, the antenna. So it's more easier to control, okay, number of beam that we required, okay, for the volumetric, and it doesn't need to have the terminations, the 50 ohm, for example. Okay, so this is some example from my students. So we did volumetrics. Okay, this is undergraduate students' work. He managed to fabricate. Okay. So, okay, so this is the configurations, the coupler and the phase shifter. So it doesn't need a power divider, just coupler and phase shifter. Okay, so this is the substrate that we use. Okay, okay, then let's take a look. This is the coupler. The students actually design. So we need to use 3 types of coupler. Basic coupler, okay. Okay, so this is the results of the couplers. So we able to actually get good results of couplers. We designed this at 26 gigahertz. Okay, so we need to do some studies on the phase shifter. So we need to control the length, okay, of the transmission line. So we need to do one by one on this one. Okay. And then this is the antenna. Okay, so we use 4 antenna, 1 times 4 linear array. Okay, then we combine everything. Okay, so this one, sorry. So this is the CST layout, and this is the one that we fabricated. Okay, so the size very small because it's at 26 gigahertz. Okay, so this is the results from the Noller matrix. Okay, so this is the beam. Okay, so by controlling the input, so with different input, we're able to have different directions of the beam. But we have problem. Okay, so we forget to control the distance between the antenna. Okay, so we have the problems with this side lobe. Okay, but I think that's for undergraduates is very good. Okay, it's very good designs and results. Okay, so that's all. I hope that you learn something from the sharing sessions. Okay, thank you so much.
Professor, can you sit there? Thank you for Professor Norhudah for the presentation. It's very fascinating. And Professor Kamal, I invited you to the stage for the question and answer. So before we start question and answer, let's have a big applause also for both of them. Is there any question from here? Okay.
Okay, introduce myself. My name is Hendrik. I want to give you a question. So, will its BTS in the future will have the small smart array antennas that use metamaterial, and will every user have benefit equally if this happens? Or will smart antennas only position themselves to maximize their coverage and capacity? Thank you.
So,
So actually, for the antenna array, it's not necessary to use metamaterials. Okay, so metamaterials is actually a design technique that's been implemented to actually enhance the performance of the antenna. Okay, so usually we have a lot of difficulty when we have the array. For example, okay, isolations, mutual coupling between the antenna. Okay, so there's a lot of technique to reduce the mutual coupling. So one technique is unequal distance between the antenna, and then we can have like turn off the sums of the, we call it bad elements in the array. Okay, we can turn off the others. Let's say we have 64 elements of the antenna, and we identify, let's say we have 4 bad elements, so we can turn off that. Okay, another technique is metamaterial. So metamaterial is not a must, but it's technique to enhance the antenna performance. So that's we can actually, because there's a lot of problems when we have a lot of antenna. Mutual coupling, side lobe. You see, that's when my student design, we have high side lobe, where we supposed to reduce that. So the techniques that can be implemented is metamaterial. But with this smart antenna, definitely. Okay, so in terms, because we went, let's say for 5G, the goal is to have high speed, high capacity. So one of the things that we need to do, okay, is to use multiple antenna, more antenna. We call it massive MIMO, okay, array of the antenna. So to give higher and very directive beam towards the user. So that's the user, let's say previously is only received, for example, 1. Now it can receive 10. Okay, more. Okay, so with that, we can actually provide high capacity, higher speed. Okay, so I think
I think the question is okay. So the metamaterial can enhance the performance of the antenna itself. Okay, so before I ask again, there was a question from Zoom. I think it's for Professor Sharul Kamal and Professor Norhudah. In 5G or 6G technology, what is the best mechanism when a user is moving? Is it using multi-beam forming antenna or using a phase array antenna where beam forming follows toward the movement of the user? Which is the best for the 5G and 6G? Phase array or switch beam, the multi-beam?
Phase array is actually we change the phase. So let's see which one is the best, because what we have, I believe now, is combinations between the static, okay, and the one that's moving. Okay, so which one is the best practically for the, let's say, high speed moving user? Is it speed train, something like that?
He only said it's moving.
Moving. Okay. So I think that it depends on the design. It can be a combinations. I'm also not say that the statics actually better or additive better, but because when practically there's a lot of things need to be included. Okay. So cost, okay, and also how well they actually able to design at the front end. Even though a switch beam, okay, we still need algorithm to support the switch beam system, okay, because we need to the system to run automatically, so to switch the ports, the input ports. Okay, so for the additive array, so it's very good if we have to enable a good RF at the front ends and also a good algorithm. Okay, so it's more costly. So I believe that the manufacturing field, the operator will choose the best options at where they need to place the base stations.
There will be a lot another factors, not only moving but moving with what we train with. Yeah. Definitely,
yes.
Okay, maybe I just add a bit. So basically, when we are talking about the switch beam, yeah, I think so. Basically, we have like array of antenna. So usually we will use like pin diode or some kind of the methods, yeah, right? So in terms of the, let's say we're talking about maybe massive MIMO, right? So let's say we are talking about pin diode, yeah. Then basically in terms of cost, it will incur more cost, yeah. So basically what I've read, I have based on the literature review, basically we have seen like array of antenna, maybe planar or maybe array of antenna, right? But basically in addition to that, they also use like adaptive. Yeah? Adaptive is actually much more interesting, yeah, because currently in terms of the hardware, I would say that it can reduce in terms of hardware, because more hardware then more cost for that, yeah. But let's say we have like array, yeah, instead of having like pin diode, right, but we are using like maybe digital beam forming, yeah? Then I think instead of having put on extra cost in terms of the hardware, then basically we can also reduce that. So basically, in my opinion, future, I think let's say we're talking about maybe huge of the array, right? Then I think the adaptive will be there, I think. Yeah, because like what Dr. Dah said, right? Like just now we are talking about mathematics, yeah, like 4 by 4. But let's say we want to have more beam, then I think we can make it to be like 8 by 8, 16 by 16. But in terms of the complexity, it will be very, very complex. But let's say we are using like just array of antenna, then basically by use it adaptively, right? So basically it will be much more easier, yeah. And then nowadays also we are talking about machine learning, this kind of thing. So basically, you know what, maybe it can make it to be much more better. But this is just my opinion. Yeah.
Okay, thank you, professors. And there's another question from here. Okay, could you give the microphone to your friend?
First, I want to say thank you for both presentation. It was very insightful. So, let me introduce myself. My name is Rusdi. I want to ask you about how antenna technology development and cellular communication development or wireless technology affect each other. For example, maybe 5G or 6G needs some requirement to achieve, like data rates or bandwidth that needs to be fulfilled. Is it the requirement first or the antenna technology first, or is it can affect each other or something like that? That's my question. Thank you.
Okay, you can.
So when first people actually studies about MIMO, I think that's I heard about MIMO when I did my master. Is in 2005, it's very long time ago, and at that time there's no implementation using the array yet, antenna array yet, except for Yagi Uda. Okay, so the research for me, the research will come first, because the people who actually set the standardizations is the people working in the industry and also the academicians who did the research. Okay, so it based on the dreaming actually. Even we see that the 5G, we dream a lot about the 5G, but we still not sure how far that we can implement our dreams. Okay, there's a lot of dreams. So we did a lot of research where actually we think that it can be used probably in 10 years, 20 years coming. But you know that sometimes it's very difficult to implement it straightly. Okay. So a lots of things that been researched probably 20 years ago. Now we see where we going to implement that. So we are researchers, so we are dreaming a lot. Okay, and we also the people who set the engineers. Okay, set the standardizations. Okay, we going to work in this industry, and we going to actually set we're the one that we're going to what the people needs, what people want. Okay, so however, we still need to base on the standardizations. So probably we dreaming first. Okay, we do lots of research based on our dreams. But in terms of practicality, we still need to base on the standardization. 5G, 6G. Okay, so now when we do for 5G, we base on the standardizations. Previously, it's quite open. Okay, now we more specific. We have the frequency, we have the specifications of the gains, so we become more clearer about what we need to do to actually contribute to the actually society, the community, to the industry. So it become more clear based on that. So it can be do it earlier, and also based on the standardizations. Okay, that's my input.
Okay, Rushdie, I think that one is actually a very good question. Which one is actually coming first? Is it standard or is it the technology, right? Okay, basically, I'm actually quite lucky now because I also involved in one of the working committee for, this 5G here. So in one of the event, basically we have come out with the standard for one thing. Then suddenly, due to the industry, because in Malaysia we have few telcos, and some is actually very strong. Then when this company is not satisfied with the standard that we have come out, then they officially come to the regulator. They say, okay, can we revise it? So basically, this is one thing. So it shows the industry really play a very important role. And the other thing is actually when I had a chance went to Japan last time before 5G was started. I think I went to Tokyo Institute of Technology, if I'm not mistaken, in that university. So 5G is not there yet, but the researchers over there, they already come out with 5G's antennas. So meanings, I don't know how is it, but I would say that the professors there and the industry, they actually play a very important roles. So meanings, what they already studied about that, but at the end, it is actually the industry that really, give a say whether, okay, we want to proceed, okay, we want this standard, these kind of things. So in my opinion, technology is there, but in my opinion, industries is actually the one that really drive, this technology actually. This is actually from my observations. So I think, thank you, Rushdie.
Thank you for the answers. Thank you.
Okay, thank you, Professor. And one more question from Zoom. Sorry, I cannot read all of the question. Maybe this is for Professor Sharul Kamal. What is the biggest common obstacle that occur during handover in cellular communication that can have a fatal consequences, and how to overcome them? Is it by reducing coverage or by creating a subcell?
Okay, so I think thank you for the question. I think very good questions. So basically, from what we have seen, that handover is actually one of the factors that make cellular to be more interesting. Meaning we are not static, we are not fixed, but we actually moving, mobile, right? So, but whenever we have different people that move in with different speed, this one will cause stress to the system, because as we understand, in our channels, not all the channels are used for communication. Some is used for synchronization, the other one is used for controls. So in order to avoid stress, whenever we have, because sometimes the cell is actually very small, but when we have too many handover, then I think in order to avoid that, basically, as what we had discussed, I think we are talking about the umbrella concept. So we divide people who are actually moving slowly. For example, let's say I'm actually walking from here to maybe UI stations. After this, maybe I walk. So maybe it's good for me because I will not be doing this handover, because because my speed is very slow. But let's say later on when I use the train, the kereta api, the train from UI to Manggarai, so maybe the speed is actually very high. So with that, then basically I think it will good, for the umbrella concept, where higher cell will be used, for the higher speed. So I think that is actually the concept that will be applied. And then I think this is actually a practical kind of things, which I would say make sense. Because what do you call that? Slow speed, it requires less handover, but higher speed will require higher handover. So I think this is something I think that where the whole concept, the umbrella concept is actually play a very important role.
Okay, so I think that's the last questions for today event, and let's have a big applause for the professors. And before we end this event, I would like to invite Professor Fitriuli to give a certificate of appreciation, and we will have a photo together.
Thank you.